All right, so what we're looking at, not lurking at, looking at, is the concept of differentiability. All right, so if you remember in the last unit, there was a bunch of limit questions, and then there was a question at the end that asked if a function was continuous. All right, so that's still in play. We need to know that. All right, that comes into play for these kind of questions also. So a lot of this is going to seem like a repeat of that. In fact, that's the first step towards determining differentiability. Differentiability is a fancy word, but all it means is derivativable. Right? You could find the derivative of a function, but it's not always going to be meaningful.
Why would they not want to say derivativable?
I don't know. It rolls right off the tongue. I think it's perfect. Derivativable. I mean, once you get the hang of it, it's you stumble over it the first couple of times, but then once you say it, it's like nothing. So, yeah, you got it right. Yeah, derivativable. Derivativable. All right. So that's going to be our challenge here. Unfortunately, or fortunately, depending on your perspective on these things, it's going to involve limits. All right. So if you like limits, fortunately. If you don't, unfortunately. So first thing we have to account for is continuity. If a function is not continuous, it will not be differentiable. So that's our easy way out. Make a determination of whether a function is continuous or discontinuous. So they're asking us specifically to determine if it's differentiable at the point x equals 0. That is not a highlighter. That is a highlighter. So what I'm going to do is I'm going to evaluate my function f of x is equal to 2 over x. I'm going to evaluate it for where x is equal to 0. All right, and that's undefined. All right, very important. Your function needs to exist at that point in order to have a tangent line at that point. All right, so it's like, how can you have a slope at a point if there's no point there to begin with? All right, so this is saying there's no point there to begin with. Now you could do other things with this, but the very first step in determining continuity is determining whether the point exists itself. All right, so no point exists at x equals 0. Therefore, function is not continuous at x equals 0, making it not differentiable at x equals 0. Because we have to address that. If you just say it's not continuous, you haven't answered the question. All right, not differentiable all right, so spelling's not that big of a deal, as you've seen with my my typo bonus issues. But generally, if the word is spelled out for you in the question, you probably should spell it right. I mean, my penmanship is crap, so even though I spelled it right, that my ER looks like an A, so it looks terrible. But you should have a fighting chance of spelling it right. The reason I bring this up is because, I mean, the spellings that I've gotten for differentiable, I don't take off for it, obviously, but I do judge the people. I'm like, how'd you come up with that? Okay. The same thing with parallel. The number of people that have written parallel, when the question asks you to determine if the two lines are parallel and it spells it out for you and you're right, like, they are not parallel, I'm like, oh, okay.
They're not parrot.
Yeah, they're definitely not parrot. So I don't get upset about stuff like that, but my wife flips out on my son pretty much every time it happens. So maybe I'll bring her in and have her yell at you all or something. I don't know. She's good at that. So the discontinuity, we know that that's a break in the graph. Leads to a point of non-differentiability. All right. So that is straight up taking something from the last unit and just repurposing it. All right. We just said in the last unit, we learned how to find continuous functions. Well, now we're just saying if a function is not continuous, then it's not going to be differentiable. All right. So in number 2, it says determine if the following piecewise function is differentiable at x equals 0. So same instructions. And then if so, what is the slope of the tangent line? All right. So now we're getting to the idea. It's like, well, it's going to be continuous because there's that follow-up question. All right. So, but let's play that out. So the first thing I'd have to do to justify continuity is I have to make sure the function exists at that point. So f of 0. All right. The relevant piece would be the second piece because that says x is greater than or equal to 0. All right, the other piece doesn't involve a 0, so I would ignore that one. So I'm going to say 2 times 0 plus 2. This is an existence verification. I just want to make sure that there is a point that exists at x equals 0. All right, in this case I get a 2, so that's a check. All right. So the point exists. Now I need to make sure that the two pieces are going to meet up at the same location. Otherwise, there's a jump discontinuity, right? So what I have to do is find the limit as x approaches 0 from the left of f of x, and find the limit as x approaches 0 from the right All right, so this is all last unit. I haven't done anything related to derivatives yet. So, plug in a 0 for the left piece, I get a 2. Plug in a 0 for the right piece, I also get a 2. All right, so the function is continuous, all right, because the function exists at that point and the limits are approaching that location, all right? So it's coming together at the same point.
But you're still using the highlighted equation, right? That's the one you're saying.
Well, from the left, I'm switching to the left equation, and from the right, I'm going with the right equation. So top is left, bottom is right.
You just plug in the 0.
And then just plug in a 0, yep. All right, so we know we have continuity, right? So I said earlier that if a function is not continuous, then it won't be differentiable. But just because it is continuous does not automatically mean that it's differentiable. All right, so now I have to test for differentiability, basically doing the same exact thing, but with the derivative function. All right, so what I'm going to do is I'm going to figure out f prime of x. All right, it's not difficult with a piecewise function as long as the pieces themselves are not difficult. So basically you're just taking the derivative of each piece separately. All right, so what's the derivative of 2? 0, it's constant, right? Derivative of negative 2x? Negative 2. Derivative of x squared? 2x. All right. Derivative of 2x? Just a 2. Derivative of 2? 0. All right. For linear expressions, we're just taking the slope. For constants, they're going to 0. for other types of power functions, we're applying the power rule. All right. So now I just have to indicate what my conditions are. If x is less than 0. If x is greater than or equal to 0. All right. So I have my derivative. I need to make sure that the slopes are going to jive from the left side and from the right side. Meaning, I have to take the limit as x approaches 0 from the left of my derivative function and see if that's the same as the limit as x approaches 0 from the right. Of my derivative function. All right, so what's the derivative, or I'm sorry, the limit as x approaches 0 from the left? So x approaches 0 of this function, negative 2x plus, negative 2 plus 2x. What do we say? Negative 2. What about the other one? Just the 2, it's constant. All right, these are not equal. All right, they need to be equal in order to be differentiable. All right, so what we have here is a contradiction. All right, contradiction. All right, in order for there to be a slope of a tangent line at a point, well, it would have to be a single slope. Here I just came up with two different slopes, but at the same location. All right, it's a contradiction, which means that I don't have a way of determining what the singular slope is at that particular point. All right, so what we would say is it is not differentiable at x equals 0. All right, it was continuous, but it was not differentiable. Oh, cool. All right, so that's kind of annoying because really, if you think about it, in order to determine that it was not derivativable, we had to find the derivative. So imagine you have a function that's a lot more complicated. You'd have to do all that work just to find out that it was not necessary to do all that work. Well, actually, the answer to that is no, because we come up with this concept of a corner, which is really just related to a piecewise function specifically. There are exceptions to everything, but generally, if you're looking at a piecewise function, you're dealing with any case where the two pieces or two pieces of that piecewise function come to a point. All right, so two pieces of a piecewise function come to a point. All right, so in this case, it might be kind of tough to see, but you're looking at a parabola, and I can just kind of rough it out. I'll just do a very, very quick sketch. You're looking at an upward-facing parabola, something like this, and then a linear function, something like that. All right, and it may not seem like it comes to a point. It's not. But it is. So it's not a smooth transition from one curve to another. All right, so it actually is coming to a point. If the more quality you put into the diagram, the more obvious that'll be, but that's the idea. So if it were just a smooth transition from one to the other, then that would be fine. Like, for example, if the other piece of the function were, if it ended up being 2 plus 2x, that would have worked. Because then the slopes would be the same. It would be a smoother transition from one to the other. All right? So, and you can look at the graph. Graph's pretty useful when it comes to this. The issue is that you're not looking to create the entire piecewise graph on your calculator. What you're trying to do is actually just kind of reason it out a little bit. I'll show you. So let me see. The original function 2 minus 2x plus x squared. And then 2x plus 2. So graph. And so I'm just going to look at the parts that are relevant. And that would be, I'll just do a quick map. Because I could just trace over it. So I'll just save it. Actually, I wonder if I could just copy it. I know I could do that, but is there a no? That's what the issue is. Not picture. Dang it. Existing. All right, so this is what the diagram should have looked like. And you can see, like, my rough diagram doesn't really do it justice. But now this is not the piecewise graph. This is just two graphs simultaneous with one another. But if I just highlight the relevant pieces, so this guy here and this guy here. All right, that's our piecewise graph. You can see, I mean, it's not quite a perfect V shape, but it does seem to come together at a point. All right, any graph that comes together at a point is going to be non-differentiable at that point. So you have a nice visual way of making a determination because you know how to look at a graph and decide whether it's continuous or not. Now you have a way of looking at a graph and determining if it's differentiable or not. The only question is, can you carry out the analytic approach of actually doing the work to justify it, right? Now, what I said was if I had made a slight adjustment to the problem, making it 2x, and I just kind of figured this out on the fly, so it's, you know, with me that's dangerous, so I could be horribly wrong. I'm usually right though. So I changed my function from 2 minus x plus x squared to 2 plus x squared because my derivative here, oh, actually it was 2 plus, what was it, 2x, right? I think I deleted too much. Because the original one was 2 minus 2x. Yeah. All right, the derivative of this would be 2 plus 2x, and the derivative of this is just 2, and if you plug in a 0, you get 2 in both cases. So let's take a look at this graph. If I just focus on the relevant pieces of this function, and again, I'll just pop it in there. You could see it's a smoother transition from one curve to the other. All right, so that's a case where you would have a piecewise graph that actually plays out to be differentiable, right? So the moral of the story here, and it's very important because people have botched this before significantly, and that is, it's crooked. That's weird. Yeah, that all of that is weird. Like, I could have lived every day of my life without hearing that commentary. I dare not repeat. All right. So, on this side here of 0, I have the parabola, and then it turns into that linear function after we hit that intersection.
Wait, is this the same thing?
No, I changed it so that's what I was saying before. If I just made the slight adjustment to the function, instead of 2 minus 2x, I make it 2 plus 2x. then it would work out that this actually is differentiable. So a very slight adjustment makes it work out. And so if you compare the two graphs side by side, so this is a change. This would be if we had y equals 2 plus 2x plus x squared. All right. So this one would be differentiable because it's continuous, it comes to the same location, but you can see the parabola is smoothly transitioning into the line, all right? Whereas here, it's just a hard turn. Anytime there's a hard turn, it's not gonna be a differentiable situation. And in fact, you have everyday language that you could use to describe what's happening here, all right? It happens pretty much all the time in this class. Anybody think of what that everyday language might be? I'm starting off with one curve, and then I'm transitioning to a line.
Rate of change.
No, everyday language.
Everyday language.
Everyday, like conversational.
Swappy do.
It's chill.
That's better. I mean, if you're having a conversation with somebody, and all of a sudden you start talking about something that's
Change of lane.
not really related to what you're going off on a tangent. Okay? Isn't that literally what just happened here? So that's the diagram for it. All right. So that if your piecewise function goes off on a tangent, then it's going to be differentiable. But if it does not, if it makes a hard turn, you know, it would be kind of like if in the middle of this conversation I started speaking Spanish, like, which would be astonishing because I don't know a word of Spanish. So that would be a hard turn. But if I started talking about like road trips or something like that, because I got into rates of change and, you know, saving money on gas and things like that, and then 20 minutes later we're still talking about that's the case where I went off on a tangent. So it's a nice easy way of conceptualizing. All right. A cusp happens when you have a single graph, a single equation that has a point, right? So a single equation that comes to a point, so we could define that immediately. Single equation or function, I'll say. I mean, it's really an equation because it's not just limited to functions, but for now we're just going to focus on functions. That comes to a point. All right, so this one I'll do it backwards. I'll create the graph first to show you what the story is, and then after that we'll talk analytics. All right, so x to the 2/3 power. Just creating a graph. You see that, baby? Look at that graph. Good looking graph, right, man? It's a weird graph, definitely. Second grade birds, yeah. Honestly, that was going to be my strategy to remember what a cusp looked like. Like, how would you, if you're drawing like stick figures and stuff like that, and you wanted to draw a bird, what would that bird look like? All right, so that's bless you. All right, so that's what we're up against. It's coming to a point, but it's not a piecewise function that's doing it. All right, so a single function that comes to a point, we call it cusp. Now, it's not going to be differentiable at that point, and we're going to justify that right now. So we do have to address continuity, but continuity is easy in this case. So I'm going to find f of 0 equals 0. Well, I'll say 0 to the 2/3. I'll actually show it. Equals 0. Point exists. We don't really have to worry about the limit from the left and from the right because it's clear based off the graph that it's going to the same point, and it's a single function that doesn't fail to exist anywhere. So we could actually just shorthand notation, just say the limit as x approaches 0 of f of x, not even from the left and from the right, it's just equal to 0, all right? And so we can conclude that it's continuous. All right, so you always, it's annoying, but you always have to address continuity first, right? Because again, if a function is not continuous, it's not going to be differentiable. But now we have to get into the derivative, all right? So f prime of x, power function, what's that derivative going to be? 2/3 as a coefficient, we multiply power by coefficient, and then what do we do to the power? Reduce it by 1, so what's 2/3 minus 1? Negative 1/3. Now normally I would say don't bother simplifying, but in this case I think it's going to serve us a little better if I rewrite this as 2 over 3x to the 1/3 power. So not much simplifying, I'm just moving the x to the bottom of the fraction. But what I wanted to do is make it obvious that there is an instance for which the derivative will not exist. All right. So what I'm going to do is find any instance for which the derivative will not exist. In this case, that means set my denominator equal to 0 and solve. All right. So 3x to the 1/3 equals 0, and that makes x equal to 0. So it's undefined at x equals 0. Now the function exists there, so it's not a point of discontinuity, but it could be a point of non-differentiability. All right. The issue is sometimes it's a vertical tangent because when the slope is undefined, well, think about an undefined slope. Horizontal lines have a slope equal to what? The slope. 0. All right, vertical lines have a slope that's equal to what? Undefined. So is this undefined telling me that it's not differentiable, or is it telling me that it's going vertical? That's where the limits come into play. Fortunately, the limit process is very easy for this. If you use, I'm sure somebody else calls it this, but I'll say what I call the ruler test. So limit as x approaches 0 from the left of my derivative, limit as x approaches 0 from the right also of the derivative. All right. So the ruler test, well, it involves a ruler or pen. Start off at some point away. So we're looking for the limit as x approaches 0 from the left. So start off at some point away from the point itself that you're interested in. Use your ruler to estimate the slope. All right. So this feels about right. It doesn't have to be perfect. Move it closer. And as you move it closer, use it to continuously estimate what the slope would be. What we're looking to do is make a determination of what the slope appears to be approaching as I get closer and closer to that point. As I get closer and closer to that point, what does my slope appear to be approaching? It appears to be going to some kind of infinity, right? Yeah, it's going, well, that's the question. Is it going in the positive direction or to the negative direction? Negative direction. The slope is going downhill. But it does appear to be getting extremely large, right? So it appears to be approaching negative infinity, all right? So that's my solution from the left-hand side. From the right-hand side, I'm going to do the same thing, estimate the slope, and as I move my ruler closer and closer, where does it appear that the slope is approaching? Positive infinity. It's getting steeper and steeper, but in the positive direction, all right? So I really can't get this off the board now. It's like suction to it. This is like a fun game now. Yeah, I know, but I was enjoying myself, so yeah, I gotta do that. Okay. So.
I'm sorry. It's just continuity. different than differentiability?
Yeah, discontinuity is talking about if there's a break in the original graph.
Right, it's like those lines go at two different points.
Yeah.
And then what's differentiability?
Differentiability is talking about whether the derivative has meaning at any particular point. So here at this location at the point, the slopes are approaching two different values. Because they're approaching two different values, we're getting a contradiction, which means that there's confusion as to, well, what is going to be the slope at that point? We don't know. We can't determine it.
So it's like this step.
Yeah. So not differentiable. So contradiction. Therefore, not differentiable. At x equals 0.
So do you just go through the process? Like you start to plug in the value first, then you do something, I don't know.
It's like what we did before to find if it's continuous, like you find the limit at the point and then both approaching is in the same, then it's like continuous. It's like what we did in the last package, but then like you have to find the derivative. So if it's not continuous, you don't have
Then you
to,
stop.
Then you just say it's not continuous.
Correct.
As in, like our first step, we plugged in 0. If those became two different points automatically.
Then stop.
What do I say? Just not.
We'd say it's not continuous, therefore not differentiable.
And then you just have to find the
Now, if it is
Yeah, what was
continuous,
the second step? Yeah.
the second step in the process, once you determine that it is continuous, then you find the derivative of the function, and then we start looking at that.
why is like this one infinities and like the other one point?
Because the other ones were polynomial or linear functions, and we could actually substitute into those. For here, we had an asymptote in my derivative at x equals 0. So it's going to some kind of infinity. It's just a question of what kind. All right. So what we can get from this is a generalization, folks. This is the important part of it, where you can kind of avoid doing a lot of this work. So you got to stay with me here. If you follow this, that's great. But obviously, it's a heck of a waste of time in a lot of cases. What you do, just thinking back to some of the skills that we learned on the calculator, we know how we can get the calculator to generate a graph of a function and also the graph of the function's derivative. So what I just learned from this is that the function exists, because they're talking about x equals 0. If the function exists at x equals 0, cool. But if there's an asymptote for the derivative at x equals 0, then I know I'm dealing with it'll turn out either a cusp or a vertical tangent. So what I'll do is I'll turn on my derivative graph. And I'll take a look at them both simultaneously. All right? So you can see my derivative graph, ruler test is great, but if I have a derivative graph coming from the left, it's pretty clear to see that it's going down to negative infinity. It's going up to positive infinity. But I like the ruler test because then you could feel what these negative infinities and positive infinities represent, because it really is talking about the slope. And most of the time, if I were to ever jump to this, just showing the derivatives, they're like, yeah, that's cool. I don't know what that negative and positive infinity means. All right. So think about a question like this on a test. Determine if it's differentiable. And I don't tell you to do it analytically. You just have to put the function in, look at the graph and the derivative. Point exists at 0, continuous. Doesn't exist for the derivative, so maybe it's a cusp. But it could also be a vertical tangent, all right? And you wouldn't have to do any of this work, all right? But this is the justification for all of that stuff. Now, this is going to be a contrast with the next example, which seems to be pretty much exactly the same, except it's going to have a different conclusion.
So once we find if it's continuous, we just have to figure out if it's a cusp or a tangent.
Exactly. All right. And so in number 4, you can see that it's going to go the other way. We have, it's a continuous function because if I find f of 0, I'm going to get a point that exists. And if I find the limit as x approaches 0, I'm going to get a limit that exists. You can also look at the graph. When I take the derivative, f prime of x, what do I get? negative 2/3. All right, so you carry out the algebra in this, you write, rewrite it as 1 over 3x to the 2/3. You can see it's pretty much the same structure. So that's my derivative. If I set the bottom equal to 0, because again, that's the only thing that's going to make it undefined, set denominator equals 0, we're going to get x equals 0. All right, so it's the same concern. So what I would need is the limit as x approaches 0 from the left of f prime of x. And I need the limit as x approaches 0 from the right also of f prime of x. All right, so that's where my calculator comes into play. Make it x to the 1/3 power instead of x to the 2/3 power. I'll look at the function and its derivative simultaneously. When I create the graph, the black one is the one that exists, the original function, and we can see that that confirms continuity. The other one is the y4. So we put that in and we never delete it. All right, always leave that on. And you can see that from the left and from the right, it's going to infinity.
It's always x equals x.
X equals x, yeah.
And then, like, I guess in terms of the test or something, is it gonna be x equals 0 always?
No, it could
Determining
change.
If it's differentiable?
Yeah,
It can change.
it could change.
So you would just plug
Whatever the number
like,
is.
if it was 3 or something into like.
3 takes the place of all the zeros, yeah.
Okay.
All right.
The derivative thing in your calculator?
Math 8. You put that in y4?
Just like keep it there. I would
Yeah,
keep it.
never delete it. Just leave it there. All right, now if you wanted to apply the ruler test just to get a feel for how this works, from the left, as you estimate the slope, you can see that it's pitching upward towards positive infinity, but then as you come in from the right, you could also see that as you work your way towards 0, it's still pitching itself upwards. All right, in both cases, it's going to infinity. All right, so we don't have a contradiction here. The limit exists at infinity. All right, in those cases, what you're looking at is a vertical tangent. All right, so these are the same. Therefore, we're looking at a vertical tangent. All right, so graph exists. But goes vertical at a point. All right. So graphically, it's pretty easy to determine, but in terms of the analytics of it, it could be a little iffy.
So when like describing graph, would you say it's differentiable in general? Would you say it's differentiable at x?
You'd say, in this case, since the only point that was of concern was x equals 0, we can now say it's everywhere differentiable.
Okay, so if that one point is always.
Not always, but since we were only worried about one point in the graph, everything else was going to work out just fine. The infinity's coming from, if you look at the derivative graph, as you come in from the left, with your ruler you're going from the left following the curve. You start going positive, and from the right, it's also going positive. So in both cases you're pitching upwards. But then that's confirmed by the purple graph. Yeah. Yeah, definitely. It takes a little time. No problem. You're welcome. Have a good one.